way. Okay, and let me now share the screen. And then I will go to the presentation. Okay, unexpected relaxation features. When I got the idea to tell you something about how relaxation data can look like, I thought that I will be quite original and that nobody will tell you that before. But it turned out that actually what I'm going to talk are not really unexpected for you anymore. However, maybe anyway, you will find it interesting. Well, the so-called quadruple relaxation enhancement. Look, we even do not know what the system here is, and I will not tell you. Expect that, well, actually, if you go to this paper, you will see what it is. It's one of our papers. However, what you see here is a kind of data which, well, shows very strong dependence on the resonance frequency, because the low frequencies is above 1000, which actually it reaches the limit of fast recycling relaxometry. And here it is below 10, so you know it's more than 2 orders of magnitude. Therefore, I used here logarithmic scale. And you see here bumps. Saying it in an elegant way, we see a frequency specific, because this effect appears at specific frequencies, frequency specific relaxation enhanced. Yeah, because the relaxation rate is enhanced, increased here. Then here you have an enlargement of this effect. This is important also before I explain again what it comes from. This is important also from the experimental point of view, because we have here 3 peaks, and those peaks are quite narrow. So you see how many points we needed to collect here on this curve to be able to really clearly see the shape of those quadruple relaxation enhancement effects. What happens typically that people just, do not perform the experiment for so many resonance frequencies. They, for instance, use 40 or even 30 points. Here we have like 100, even more. So what happens typically is that you see here in this range some irregularities. So I have to say that for quite a long time, those effects were omitted. Why? Because, well, if the experiment was not performed with very small frequency step, there were just a few points which somehow did not follow the curve. So the initial thought of people was, this is some scatter here. I don't know what is happening here. Let me ignore those points. Well, so those points were ignored, unfortunately. So if you investigate literature and you look some years back, there will be, and compare the data presented there with data for similar systems, which are relatively recent, you will be surprised that such effects were only very rarely reported in the literature. Eventually, somebody said the king is naked, And then one needed to acknowledge that such effects do exist. Especially if you perform experiment in a very dense way. The thing is that if you expect, and when you can expect such effects is a different topic, but if you expect such effects, you really need to perform the experiment with a very small step in sequence. However, come on, this will be a kind of paranoid, and in this way, nobody will perform any resonate experiments. Because after all, okay, maybe here the relaxation is fast, but here the relaxation is very slow. So imagine how much time collecting such a data takes. It requires human power, time, energy, consumption, everything. And first of all, this also occupies the relaxometer time. And the worst thing which we could do is that if there's many projects and many people waiting to perform experiments, and then you run such a thing for the whole day or even 2 days. So one has to be reasonable. First, I mean, we have here those data, but this is not the best practice, let's say. What one should do, one should run such experiment with a larger frequencies, because actually, after all, here you can really increase the frequency step. One does not need so many points, neither there nor there. However, there will be a range in which you will see a kind of scatter, some deviations from what you expect. If this happens, it means that very likely you have quadruple relaxation enhancement effects, and then you can select this range of frequencies in which this effect appears and collect more points in this range. So this is, I think, very practical piece of advice, how to effectively use the time and really collect the data which we need. Okay, but such thing is present. You see here, actually, if you look more carefully, that I applied here this concept of decomposing the relaxation data into relaxation contributions associated with slow, intermediate, and fast dynamics, plus a frequency-independent term. But in addition, I have a relaxation contribution which accounts for the presence of those peaks. What is the story behind? During my first lecture, I told you that nitrogen 14 has spin 1, not spin 1/2. And you remember we discussed the possible orientations of the magnetic moment, that this is 0, 90, 180, yeah? 0, pi half, pi. So we have 3 orientations of the magnetic moments with respect to the magnetic field. And this also means that we have like 3 variable energy levels for nitrogen 14. So the first information is that for biological systems, organic systems, well, it is not the right word, for biological systems, very likely the presence of nitrogen 14 will lead to such effects. Look at that in this way. There is a dipole-dipole coupling between hydrogen atoms, protons, yeah, because proton is the nucleus of a hydrogen atom, between protons and the nuclei of nitrogen 14. Dipole-dipole coupling. And we apply magnetic field. The proton magnetic moments of protons can take only 2 orientations, parallel or anti-parallel. And as we already talked about it, the gap, the difference between the energy levels if you express it in angular frequency, in frequency units, gives you the resonance frequency. And we also said that actually with increasing magnetic field, yeah, the resonance frequency is proportional to the magnetic field. So if I would draw a kind of hypothetical figure, in which on the x-axis, there's many of such figures in the literature. In the x-axis, I will have magnetic field, and on the y-axis, I will have the resonance frequency. This will be just as simple. I mean the proton resonance frequency. So I can clearly say that the difference between those two energy levels are proportional to the magnetic. But what happens for nitrogen? For nitrogen, the first thing, I have not two, but three energy. Second, nitrogen nuclei experience a different kind of interaction. This is called quadruple interaction. You can read that nuclei which possess spins larger than 1/2, so 1, 3/2, 2, and so on, until 9/2, possess so-called quadruple moment. And the quadruple moment interacts, it is related to asymmetric distribution of charges, and this quadruple moment interacts with electric field gradient. This is not magnetic interaction, this is electric interaction. However, what is happening? The energy levels, those three energy levels of nitrogen-14, depend not only on the external magnetic field, but also on the quadruple count. And I can tell you that actually, because the geomagnetic factor of nitrogen is quite low, I still didn't check it, we had this discussion with Carol, it's quite low. I don't know whether it was about nitrogen or carbon, but I have in mind nitrogen-14. So, but definitely, geomagnetic factor of nitrogen-14 is very low. Then, at low and intermediate magnetic field, the coupling with the external magnetic field does not matter much. In fact, the energy levels of nitrogen-14 are mainly determined by the quadruple interaction. And the quadruple interaction is independent of the magnetic field. So what is happening? When I change the magnetic field and look from one side at the resonance, at the gap between the energy levels of protons, which is nothing else like the resonance frequency, I will have a linear dependence on the magnetic field. When I draw a similar figure in which I will have on the x-axis magnetic field, on the y-axis, I will have differences between the energy levels of nitrogen. Attention, they will be free values, because if I have energy levels 1, 2, 3, there will be difference between energy levels 1 and 2, 2 and 3, and 1 and 3. So I will have like free dependence. So the differences between those energy levels will be, in fact, almost independent of the magnetic field. So the conclusion from that is quite simple. I have energy levels which are independent of the magnetic field, so they are like flat. And this is one side. The second side is that I have the resonance frequency, which linearly changes with magnetic field. So one can easily guess that at some magnetic fields, the line representing the resonance frequency of hydrogen atoms will cross those lines which represents the energy levels of nitrogen-14. And as we have three energy levels of nitrogen-14 because of the spin 1 of this nucleus, this crossing will appear. So this explains why we have three relaxation maxima. In other words, one can say it in this way. I mean, it explains why there are three effects, why there are relaxation maxima. I mean, maxima of the relaxation rate is a difference. Let's assume that those energy levels cross. What is happening there? We are in a kind of resonance. I mean, it's like, it's competing intents. So normally, the hydrogen magnetization is lost because of it's losing its magnitude because of the relaxation. Yeah? But at those specific frequencies, when the resonance frequency of protons matches one of the gaps between the energy levels of nitrogen-14, I would put it in this way. Nitrogen-14 somehow takes over the proton magnetization. I do not want to go deeply into quantum physics. It's a kind of naive picture, but this is, one can visualize this effect in this. So it's like additional thing, it's this normal relaxation process, which goes via proton-proton dipole-dipole interactions. And there is also a relaxation process, which comes from proton-nitrogen interactions. But this relaxation process is not much efficient because the geomagnetic factor of nitrogen is low. So the proton-nitrogen dipole-dipole coupling is much weaker than proton-proton dipole-dipole coupling. So you can see here that really this contribution is not much efficient, except of those frequencies at which the resonance frequency of protons matches one of the gaps of between the energy levels of nitrogen. Because then the nitrogen somehow recaps and competes in the relaxation process. So then under those conditions, nitrogen is able to steal a part of the magnetization from protons. Well, but looking at this from the perspective of the protons, it's like the magnetization decays faster. So one can say, yeah, if you analyze the data in this way that you look at proton magnetization versus time at different frequencies, and then you figure out that at some frequencies, the magnetization decays much faster, yeah? For instance, okay, I look at this frequency and I get a certain relaxation rate. Then I look at this frequency, I look at the time dependence of the magnetization, and I figure out that the magnetization decays much faster. So if I just feed my exponential or almost exponential function to that, the faster decay will be interpreted as a faster relaxation. It means a larger relaxation rate. So in this way, we'll obtain a local enhancement, frequency-specific enhancement of the relaxation rate. Therefore, in such systems, one should consider proton-proton and proton-nitrogen dipole-dipole interactions. And the proton-proton dipole-dipole interactions will give you most of this curve. Like proton-nitrogen will be mostly relevant, this coupling will be mostly relevant at those specific frequencies. You know, there's a trick, namely, when you think about positions of those maxima, the position of this one, this frequency, is given as a sum, as a difference between those two frequencies. So this frequency minus that frequency, this value, corresponds to the position of this one. Then how to describe such thing? Oh my God. You see here, you have a collection of experimental data for different kinds of proteins. Yeah? All of them show this kind of effect. I have to say that this was extremely difficult to collect the data because, well, the relaxation process here is very fast, but it's not only that. You will learn during the experimental training which effects are challenging from the experimental point of view. And what we have here, as I told you, because the data here, this is not one of those examples, this is something else, but it can be also one of those, yeah? So we have two relaxation contributions, one originating from proton-proton dipole-dipole interaction, and one originating from proton-nitrogen dipole-dipole interactions. I am not going to talk much about the mathematics, but if you see it here, this proton-proton contribution here is nothing else like a sum of three Lorentzian-like contributions, slow, intermediate, fast, plus a frequency-independent term. And here, there's an analytical expression divided by Pascal Fries. This word became very popular to describe this fact. Well, this equation looks like it is very complicated, but in fact it is not. But let me explain it step by step. Before I do that, I would like very much to warn you that this expression applies only under very, very, very limited conditions. It will be too complicated at this moment to discuss those conditions. Maybe in the course of time, we'll eventually do that. However, well, it's worth to know that there is such a possibility. You see, here, it's a kind of prefactor, which is in fact similar to the definitions of those dipole-dipole couplings. This dipolar relaxation constant. It would be worth at a certain moment to write explicitly expressions for that. However, what we have here, we have zero magnetic factor of proton, zero magnetic factor of nitrogen, well-known physical constants, yeah, like magnetic permittivity or Planck constant. And here is a kind of effective distance between hydrogen and nitrogen atoms. Then here are a kind of simple trigonometrical function. The only tricky thing is what theta and phi means, but then we'll come to. Here you have, in fact, three Lorentzian terms with a correlation time, just a moment, and three resonance frequencies, which are labeled minus, plus, and 0. Actually, of course, one can immediately conclude that 2 pi ni minus can be described like omega minus. Here we can have omega plus. Here we can have omega 0. Unfortunately, sorry, I cannot. Just a moment, something strange happened because I wanted to edit this equation, and I cannot. This is just to remind you that you are dealing with angular frequency. Those frequencies that we call it omega minus, omega plus, and omega 0 are nothing else like the positions of those quadrupolar peaks, because the quadrupolarization enhancement effects are often called quadruple peaks. Well, quadruple because they're associated with the fact nitrogen 14 possesses quadruple moment, and peaks, yeah, because they are peaks. So this position of this one is at omega plus, because this is the highest frequency. Position of this one is at omega minus, and omega 0 is for this. And omega 0 is always omega plus minus omega minus. Then you have here a correlation time, which here was described by tau rod. The index rod indicates rotation. Well, it might be like that. Generally saying, the correlation time, which is here in this equation, should be treated in a more general sense as a correlation time which characterizes time fluctuations of proton-nitrogen dipole-dipole couple. Time fluctuations of proton-nitrogen dipole-dipole couple. In practice, the reason of those fluctuations can be rotational dynamics of hydrated molecules, biomolecules, but not always. It is like this exponential correlation function, yeah? It might be rotational dynamics, but it also might be something else. So the general meaning of the correlation time, which is here, is the correlation time for the fluctuations of proton-nitrogen dipole-dipole coupling. And the correlation time might be equal to one of them, but not necessarily. This is just a kind of option, and when one analyzes the data and such effect happens, but this time will be matching one of those times, and I am pretty sure that I will never match the shortest time. It might match the slow or the intermediate one. This I will also explain why. Then this is a kind of large area, if such effect happens, to discuss what is going on in the system. But I cannot reveal everything. You must see examples and get step by step a deeper understanding. It would be too much to talk about. So it is like this correlation time can match one of them, but it may also not happen, and this will be not surprise. Then let's forget for a while about those prefactors. Look what is inside here, inside this expression. This Lorentzian function has here omega h plus omega minus. Here is also omega h plus omega plus and omega h plus omega c. It does not matter that this is omega minus, omega plus, or omega zero. What matters is that we have here sign plus, which merely means that when omega h increases with increasing magnetic field, the denominator increases, and the whole ratio decreases. So nothing really surprising happens here. However, here we have a counterpart of those terms which differ from them by the sign. There's minus sign. And look what will happen here. When this factor, this product, which is much smaller than 1, we already discussed this effect. If this product is much smaller than 1, then in fact it can be neglected, and we have just the correlation time here divided by 1, which is just the correlation knock. Then this product increases. So in principle, yeah, the whole ratio goes down, it decreases. And it is like that, it decreases. But then all of a sudden, yeah, those two frequencies match, and this means that the difference is 0. So the term is again gone. So well, this ratio explodes, yeah? Reaches a maximum. The same here and here. So this is what we have here. Something is almost frequency independent or slightly decreases, blah, blah, blah. Then we have the matching, and this ratio reaches maximum. And again maximum. And again maximum. So mathematically, you see this resonance condition here. When those two frequencies match, this term explodes. If those two frequencies match, it happens again and again. But then look, this effect only happens or is really spectacular if this term matters, and that term matters, and that term matters. Because it may happen that the correlation time is so short. So in fact, independently what we have here, this ratio, this product will be always much smaller than 1. All the time. So in such case, one would not really see any frequency-specific relaxation enhancement because, well, it's like, you know, if there is no matching, I have like 1% of contribution of this term. So really does not matter compared to 1. Yeah? So if there is no matching, this is like 0.001. So if there is a matching, is 0. So really, this effect is like legit. This brings us to the conclusion that for very fast dynamics, or well, say very fast enough to have this, to keep this product and that product and that product much smaller than 1, there's no quadruple relaxation enhancement. So if you see such effect, it means that there is a fraction of molecules for which proton-nitrogen dipole-dipole coupling fluctuates in time relatively slow. So, roughly speaking, sometimes you can say that this is a measure of immobilized water, immobilized molecules. What is the fraction of molecules which do not move? Well, I would not put it so drastic. They can move. But this is more or less the limit. They can move in a quite efficient way. The effect disappears only if they move so fast, so this product does not matter compared to one. Then Again, before I go to that, which you are probably more and more curious about it, look, now I said that this is something happens strange with my presentation, whatever. I hope you still see. So this is for omega plus, this is for omega minus, this is for omega zero. But omega zero is omega plus minus omega minus. Yeah. However, I can read just what is the position. I can see what is omega plus, I can see what is omega minus, I can convince myself that this is the difference. I can do all that. And then, in fact, if I analyze the data, I do not need to fit those quantities because I can calculate them pretty well. And then I do not want to show so much math at this moment. This can be for later. However, I will tell you only that those frequencies are determined by quadruple parameters. There are two parameters, amplitude of the quadruple coupling and so-called asymmetry parameter. If you would be interested, you can read more. So knowing those two frequencies, I can just calculate those parameters. I mean those quadrupolar parameters. And this is the thing, because the quadruple parameters have something to do with the electric field gradient. So it's like if they remain the same, you can say that actually, well, the structure of the molecule is pretty much the same. Because what is happening? Electric field gradient is very, very sensitive for even subtle changes in the molecular structure and environment. So if you see any shift of those maxima, for instance, with temperature, then you know that this is a kind of a rearrangement in the molecular organization. Then let us come to those parameters, theta and phi. There are, in fact, two angles. They're meant to describe orientation between the dipole-dipole axis. So I have proton-nitrogen and dipole-dipole axis. And is the orientation between this axis and something which is called principal axis system of the electric field gradient. Not going much into math, electric field gradient is a tensor. It has something like principal orientation in which the matrix representing the tensor is diagonal. Again, this is related to the geometry of the molecule. And you have, like, those frequencies which are determined by the quadruple parameter, the amplitude of the quadruple coupling and the asymmetry parameter, you can learn them from the position. The width of those peaks give you the correlation time, because after all, this is the Lorentzian function. Those parameters, theta and phi, give you the relative ratio between the quadruple peaks, between the amplitude of them. So one can really fit those data in a kind of way that you can be sure that this is not over-parameterized. And you can learn a lot about the molecular structure and dynamics in this way. I will stop for a while the sharing. And the question is to you, whether you have any questions to this part. Let me wait 3 minutes. maybe we will have some questions. If not, I will start with something else. Okay, I do not see questions. So in the second half of the lecture, I would like to show you something which is not really specific. So the title will be somehow misleading. However, I didn't know how long it will take us to discuss those fancy features. And what will happen before me, let's say, to which extent such effects will be already discussed. So I reserved 1.5 of hour for that. But on the other hand, being prepared that you might at this stage see this as something peculiar, but in a way I will be worried later when it happens to me. The second half of the lecture I would like to spend on explaining again but in a practical way, something what Adam told you yesterday. Adam, please do not take any offense. Your lecture was excellent. I just want to force our audience to calculate some things yourself, that you can really believe that you can do that. So I will, as I suppose everybody has access to Excel, I will try to convince you that you can write your own software in Excel to determine the translation diffusion coefficient. What I want to say is not that we operate in Excel, but even if you are far from this subject and you really do not know how to do things and you do not have access to origin matter and you never did, I want to convince you that even so, you can make a kind of quantitative analysis by yourself. And the second purpose of this demonstration will be just to show you how to calculate things, to get some practice. So let me again share screen. However, I will be in a position that I will be sharing and stopping sharing screen. And in addition, I would need to make some notes. You might like to do it as well. So let me start sharing screen. Share screen. And now, well, I will try in this way, then I will need to switch. Okay. Do you remember the story about translation diffusion? That if we have relaxation data and on the x-axis we plot square root of the resonance frequency, and on the y-axis we plot the relaxation rate in linear scale, then we can observe in the low frequency range a linear dependence. And from the slope of this linear dependence, one can calculate the diffusion coefficient. So here is the relaxation rate as a function of frequency. Here is square root of the resonance frequency, and this is the value of our slope. And the diffusion coefficient D is hidden here. So I need to copy that for myself because I will be writing a software for any software, Excel script. I over D power. Look, I have here two expressions because quite often, if you look into literature, you can find different forms of those expressions. This is one of them, and it is correct. This is another one, which shows two differences compared to that. The first thing is that here, the independent variable is square root of the resonance frequency in hertz. So it is like here, resonance frequency in hertz. However, as you know, for all expressions in terms of spectral densities, we use the resonance frequency in angular frequency units. So here I just decided to rewrite those expressions, but using here the angular frequency units for the frequency. Omega h is equal to pi nu. So this is the one. One must always pay attention what you have on the x-axis and what in which units. Then there is such a thing here. Of course, if I write things like that, yeah, 1 over d to power 3/2 is nothing else like d to power minus 3/2. This is for what Adam was explaining at the first day, and this is also obvious. But there's one more thing. Here I have D, and here I have D real trans. Well, the fact that here I have D and here I have D trans, it really does not matter because we are talking about translation diffusion coefficient. So some authors just do not indicate it explicitly, thinking that this is obvious, in fact it is. Some authors just add this index trans. Does not matter. But what is important here, is this real, because there is a difference between diffusion coefficient, so-called self-diffusion coefficient, and relative diffusion coefficient. You know, relaxation stems from mutual dipole-dipole interactions in most cases, and this is what the equation is about. Mutual means involving two parts. So let's say two molecules. Yeah, it's intermolecular dipole-dipole. If one of the molecules moves, the second also moves. So the self-diffusion coefficient describes the movement, yeah, of a single molecule. However, if I look at the relative motion of two molecules, because after all, the mutual dipole-dipole coupling is modulated by the relative diffusion. So that the relative motion, relative diffusion, is twice faster as the self-diffusion. It's like, you know, let's put it in this way. It's like relative motion, yeah? If one person does not move, only one person is moving, then you have a certain, yeah, the distance between those two persons changes, yeah, with a certain speed. If the second person also starts moving, the distance can change twice fast. Of course, it's the matter you can say about the orientation or the directions in which they move. However, anyway, it's quite obvious. If I have independent movement of two molecules, their relative translation diffusion is twice larger than the self-diffusion. So analyzing diffusion processes, one has to always be aware of that. Because if you want to compare translation diffusion coefficient with some literature data, because after all, this is quite well-known value, it can be determined in other ways. For instance, but also NMR, yeah, for instance, using so-called gradient diffusiometry, maybe at some time we'll come to this point. Then usually self-diffusion coefficients are given. So you must always know whether in your studies you determine the self or the relative translation diffusion coefficient if you want to compare it with the relaxation data. I will stop for a while the sharing because I must do some manipulation and I am shortly. My manipulation is nothing else like going to orange. I have here glycerol. Okay, let me go to this one. Workbook. As you can see, I have here a lot of data. So I have to find the right one. So I need my frequency column. And this data. Copy, paste. So here. Look, it started from 10 megahertz. And please be careful. You see that my frequency is in hertz. This is also quite common mistake that people, for instance, plot relaxation rate versus frequency in megahertz or kilohertz, and then they have here frequency not in hertz, but kilo or megahertz, and they do not realize that, and anyway try to find diffusion coefficients from that, and then they get nonsense values. Column, set column values, and they take the square root of the relaxation, of the resonance. And I plot. Yeah. And I plot, and I have quite nice linear dependence. This is no doubt about it. The question is, of course, that the quality of my feed depends on the range which I choose here. Well, this is not so easy. For instance, I'm sure that if I make it here, I can make that. Yep, I can enlarge this for myself. I know that I could enlarge it also in a different way. Okay, so it's obvious that I'm losing here the linear dependence. But well, let me try at least approximately, sorry, a stupid way, to estimate the linearity range. Let me make it like that. And I try to imagine in a rough way when the linearity can stop. Yeah, somewhere here, maybe. So I know that this is more or less here. Okay, let me remove that. This is always good to know. And then I can take the proper range which I want to use. So let's say, yeah, let us not fight for single points. And for this, in this range, analysis fitting linear. I fitted a linear function. Not bad. Let me make it so you can see. Yeah. And then let me look at the slope. It's more or less minus does not matter. Of course, it is minus because the curve is decreasing. 5, 0, 7. You know, this is another thing. You have tendency to copy numbers, not looking at units. Okay, I can think in this way. I can think in this way, but only if I ensure myself at the beginning that the unit is proper. So as I said, that I have the resonance frequency in hertz, I have the relaxation rate in second minus 1, not for instance, milliseconds minus. So okay, so I determined the slope. Then I will stop sharing for the purpose that I have to switch to something else. I am back with you. Yeah, what I have here is after all nothing else as a simple Excel sheet. And let me start dealing with the diffusion coefficient. So I have the slope is 0.507. I'm actually wondering if you can say in which units the slope is. Who knows in which units the slope is? Who can say what are the units of the slope? Look, I have a relaxation rate on one side, and this is in 1/2. Then I have the slope times square root of resonance frequency, which is in hertz, the resonance frequency, which is also 1/2. And I have square root of it. So thinking in this way, when I think about relaxation rate, the unit is second power minus 1. Then there's the slope times the units which are second power minus 1/2 because it's square root. So the slope must be in a units which are second power minus 1/2. It is really worth to ask yourself this kind of question. Then I do not know whether you have the equation in front of you. If you like, I can come back to this equation because it will be really good to have it. Maybe I will be able to paste, copy. No, this. Okay, I was able to paste this equation to the Excel sheet. So this is my step. Well, I would propose to start with simple thing, namely to calculate this value, square root from 2 plus 8 plus 5. So let me make factor, and factor 1 is equal to 2 power 1/2, yeah, plus 8 divided by 5. Yeah. This is not really a very big deal. Then I need next quantities. Mi null, gamma H. So this is the permeability of vacuum, magnetic permeability. Gamma H is the geomagnetic factor of proton, and H bar is the Planck constant. Well, I do not know them by heart, so I will have to recurse to Google. However, units here also matter. Of course, we can check the units very well, and you can do that. However, okay, we will be doing that, but not immediately. Because at this stage, it is sufficient to ensure yourself that all the units are in the SI system. So let me start searching for them. So I'm searching for Planck constant. I go to, after all, I need reduced Planck constant, which is Planck constant divided by h by 2 pi. Yeah, and this is denoted like h bar. I am writing it for myself, and I will be with you. Okay, so I'm going to Excel. So you could change it check it by yourself, but I ensured myself about the units as joule times second. And the value of h bar is 1.05 and minus 34. Okay, it does not understand it. I suppose I should put here comma. Yeah. So let me now look at the value of magnetic permittivity. So I have to go again. Just a moment. Actually, what I need is the magnetic permeability divided by 4 pi. And this is very convenient because it is just I would really appreciate if you could do that together with me because I can be very easily mistaken and it was done for the purpose of doing that together. So I'm coming here and I have me 0 over 4 pi. And then the number is very simple. Although I must know the units, which are Newton divided by ampere power minus 2. So that again, the right units. Newton, ampere, joule, second are just as SI units. So now I should go to the geomagnetic factor. So let me go to the geomagnetic factor. This is what we should know already. I mean, not by heart. Geomagnetic factor or geomagnetic ratio. Yeah. Geomagnetic ratio. Just a moment, because I want to find the proper units. So we know that this is 42.6 megahertz per Tesla. This is what I told you, that the resonance frequency is proportional to the magnetic field, and the proportionality factor is the geomagnetic ratio, the geomagnetic factor. So you see that for hydrogen atoms, when you apply the magnetic field of 1 Tesla, you will gain the resonance frequency about 40 megahertz, to be precise, 42.6 megahertz. So knowing that, I'm coming to my zero magnetic ratio, and of course I can write 42.6. Well, I'm committing now huge mistake, because this is in megahertz per Tesla. And megahertz are not SI units. Look, I operate in hertz. Everything here is in hertz. So what I need is in hertz per Tesla. Tesla is the unit of the magnetic field. It means this is e power 6. Because I converted megahertz to hertz. So I think we are ready to deal with this expression. So let me put it factor 2. And what I have here? I have that times that times that, because it's power 2, times that, and this is power 2. Great. So I have my factor 2. And then I should calculate n number. N number is the number of hydrogen atoms per unit volume. Path. The question is, per which unit volume? As we are in SI system, we need to calculate the number of hydrogen atoms per cubic meter. And our system is glycerol. So now the floor is yours. The question is, how many hydrogen atoms are in cubic meter for glycerol? So how many hydrogen atoms we have? We have, yeah, it will be more in English. We have in 1 cubic meter for glycerol. Ready to try? I'm waiting for ideas. Well, what is the molecular mass? Can somebody find the molecular mass of glycerol and put it to chat? I'm waiting. Well, no response, yeah. Roberto, 2092. And this is what is very important, is in gram. I will not put per mole because actually, well, it's molar mass. Let me put it in this way: molar mass, not molecular. So 1 mole of glycerol weighs 92 grams. What is density of glycerol? Could you please check density of glycerol? Yeah, density in gram per cubic centimeter is 1.26. Yeah. I would advise at this moment immediately switch to SI units. So molar mass in kilogram is equal that times yeah, because 1 kilogram has 1,000 grams. Density in kilogram per cubic meter. Now is your task. No? Are you sure, Roberto? Because I got 1,026. I'm thinking in this way. I have density in gram. So I have 1.26. Yeah, I can do it in this way. In a kilogram per cubic centimeter. Still. So I suppose you agree. Okay. Okay, if you agree with me, I will make it kilogram per cubic meter. And you agree with me that this is 1 to 60. So we solve our problem here. Yeah. So, okay. So I know that I know now that if I know this density, I know now that 1 cubic meter weighs 1,026 gram, yeah, kilogram. This is what I know. And I have the molar mass is 0.092 kilograms. Yeah, this is the molar mass. So what is the volume? I must make such a calculation, yeah? What I should do is equal that divided by that, yeah? And this quantity is volume of 1 mole, yeah? In cubic meter. I make a simple proportion. 1 cubic meter includes this amount of reserve. So what will be the volume of 1 mole? Yeah? So the volume of 1 mole is like that. Then I have to think next. What is the Avogadro? I suppose everybody knows what 1 mole is. Yeah, I hope this is the Avogadro number. I hope I know it correct. So Avogadro number gives me the number of molecules in 1 mole. What is the number of 1H per molecule? Number of 1H per molecule is 8 in glycerol. Yeah? So number of 1H per mole, number of hydrogen atoms per mole is this times that. So what is the conclusion? We know that in this value, in this volume, we have this number of hydrogen atoms. So what will be the number of hydrogen atoms in the volume of 1? The calculation is actually very simple. Per cubic meter, yeah? This is equal to what? That divided by that. So this is the number of hydrogen atoms per cubic meter in glycerol. So let me make it like product 1. And I will calculate. I will make it like this range factor times this range factor is the second term times this value which I calculate. So this is this thing. What I have here is pi power 3/2, but I will not do that so far. So now I can calculate this thing, pi over diffusion coefficient, power 3/2. For this purpose, I have to divide this slope, because I have it here. Now, it's the slope. This whole thing is the slope. Slope is this factor times p over d. Yeah, this slope, I have to divide it by what I calculate. So this is my value. So let me now calculate I over d. So this will be this value, power, what? 2, 3, yeah? 2 divided by 3. So I have, let me calculate 1 over d, which will be this value divided by 3.14. Let me calculate d, which will be 1 over this value. And d, as Adam explained, is in meters squared over second. So I pick, and I can be sure about those units because I kept the SI units all the time. If I need to have the relative diffusion coefficient, is just this times that. You know, maybe I'm mistaken somewhere because I was just doing this like, you know, online, doing review and so on. Maybe I omitted something here, maybe I made a mistake. After all, yeah, this is always possible. You would need to check that, I will say. But you have example that one is able to perform this kind of calculations. So I will stop sharing. Of course, you know, in practice, please do write a software for that. I mean, you can have a kind of Excel sheet, but you must make it more elegant and somehow adjust it to your own needs so you know what is what. And then you change one parameter, you change the slope, you change the molecular mass or something like that, and you get the translation diffusion coefficient. But I just wanted to make it step by step. So this will be for a while. Do you have questions? Well, I do not see any, so I will stop recording.